Hi everyone, welcome back to 4G end-to-end signal course session number 2. In session number 1, we had covered or went through the initial parts related to 4G foundation concepts, where we started from the initial U access, whenever the user is turning on his device, what kind of procedures he is going to follow until he gets into the connected mode. So we went through the P element selection, cell search, cell acquisition, until we reached into the cell selection, and we also discussed overall service selection. And in today's video, we're going to discuss the part highlighted in blue color, which is mainly related to the RACH procedures. Then we'll move into the high-level perspective whenever the user, after finalizing the RACH, how we will move from RRC idle to RRC connected. I shifted the parts to tracking area update and paging under the sessions of tracking area update and paging, just to have a complete session from the signal perspective and also the overall introduction for tracking area update and paging as well. And session number 3, which will be coming maybe two or 3 days directly after session number 2, it will be covering the high-level perspective about the mobility and radio resource control and also the network architecture, which is very, very important to understand again before going to the end-to-end thing. So now let's move to the content of today's session, because today's session will be very rich. It will be covering a lot of details about the RACH procedures, including all the parameters and these kind of things which is needed by the UE during the initial access. So here is the overall introduction of today's video session, which is session number 2. Again, this is a UE journey in the left side here. If you remember, last time we covered the part related to P element selection, cell search, and system information acquisition, where the users acquired the master information block, system information block type 1, and from system information block type 1, he was being able to read the other system information, which is system information block type 2 and others. Then we ended by the cell selection part, where the user selected the best cell or the best suitable cells, but still it cannot proceed with the signaling because this means the user is only downlink synchronized. So it means that now the user to initiate will need to follow some procedures in order to get uplink synchronized, and here where is the random access procedures come into the figure. In the random access procedures, the user will gain the uplink synchronization and also gain the uplink initial resources to be able to send data in the uplink. This is what we are going to discuss today. So in today's video, we're going to cover these 6 points. The first part, I will give you a high-level introduction about the RACH in general, just to give you a quick introduction. Then we'll start going deep dive into all the information highlighted in the introduction. For example, initially we'll be starting with the RACH call flow overview. Then for the RACH call flow view, I will be discussing afterwards the RACH parameters within SIB2 during the system information acquisition. During the system information acquisition, the user at this stage, he decoded the system information block type 2, which includes all the information related to the RACH procedures. This will be discussed in much detail. So we'll give first a high-level introduction here about the SIB2 messages contents from drive test and what it means from high-level perspective. Then we'll try to deep dive into each and every single message within parameter within SIB or system information block type 2. We'll try to give a clear visualization and also kind of detailed explanation of the RACH parameters. Then again, we'll jump back to the content within the messages from the call flow. For example, message 1, message 2, and message 3. This will jump back to it because I didn't want to make it directly after the call flow, because first we need to understand the parameters, because all these parameters will be covered partially within the messages 1, 2, 3. So this will give you a practical understanding. Also, I will be discussing some of the high-level concepts about the so-called U identities. Like, for example, there's something called RA-RNTI, temporary CRNTI, or CRNTI, or radio network temporary identifier. I'll be discussing this part as well, which is important to understand, especially for those who is working in the trace analysis. You need to understand the meaning of these terms about the U identities. Then we'll be end with the last part about RRC setup from high level perspective, because the detail would be covered within the first session about the attached procedure. So now let's move forward first with the high-level call flow. So in this slide, actually, this is a RACH overview, overall overview. The left side part, which is here, which is called RACH overview. This is covering that what kind of procedures will be followed by the users in order to get uplink synchronized. This is from high-level perspective. The same will be covered within the call flow. And the right side here, this is explaining about the high level as well, what you are expecting to get from the parameters of the SIB2. For example, whenever the user is going to send any message, for example, message number one, he needs to know at what frequency is going to send, when, at which subframe, what is the duration, these kind of things. So this will be explained as well here from high level perspective. And later we'll be covering the details about the exact parameters and visualization for each and every single parameter. So now let's see here what we have. So if you remember in previous session, we discussed till the user reaches into downlink synchronization, that now the user already acquired the cell search, he found the best suitable cell, he become now downlink synchronized, and also he read already or decoded all the system information, including system information 1, block type 1, and master information block, and also system information block type 2. So now, once he got or decoded system information acquisition, now he have now he decoded the blueprint about the required resources to get uplink synchronized or to initiate the RACH procedures. For example, at what frequency, time of send, these kind of things. So now what will happen? The user now, once he do this, the first thing the user will do, if you look into this one, he will initiate the first message, which is called PRACH or random access message. This is the first message. Usually we call it message one, and he will initiate this one in order to let the user the init B to tell them that I would like now to initiate the uplink synchronization with the init B. And again, now to repeat myself as well. As you know, initially there is no scheduling, there is no resources being allocated to the users, the UE. So all the information about when and where to send the PRACH first message to get uplink synchronized is already decoded by the user during the system information acquisition from system formulation block type 2. The content of this message will be discussed later on, but this is mainly have kind of information about subframe and other multiple information. But again, remember, this is just initiated to get uplink synchronized. So this is called message one. So once the init B received message one, so now the init B need to respond back to the users with something called message number two, or we call it usual RAR or random access response, which is this message usually contain a lot of information. For example, if you look into this message number two, which is called RAR or message two, this will be discussed in details later on as well. This is including a lot of information, including timing advance command, and also assigning a temporary radio network identifier. This is like a IU identity being assigned by the init B to the users in order to be able to differentiate or to schedule the resources to this particular user later on whenever the init B is sending any kind of data, or the UE himself is trying to decode any of the BDCH and so on. He is using this temporary radio network identifier. So it's used for scheduling and on other things as well. So, and the timing advance command, for example, usually in the first initiated message, there might be a kind of a mess or a sync between the init B and user based on the distance between the init B and the UE. So maybe the UE will be out of the slot boundary, or usually it should be at the beginning with slot boundary. So the init B need to get or to ensure that any subsequent message and uplink from the UE would be coming kind of synchronized in terms of timing. So it will send timing advance command asking the user to, for example, send the messages more early or to delay the messages, like this is just to align the timing. So this is timing advance command just to instruct the users about when and where to send the next message, especially in terms of time. So this is to get more synchronized with or have a more synchronization in terms of timing between the init B and the UE. So once the user receives this message, now the user needs to respond with something called message 3. It have a different terms, but usually this is mainly the RRC connection setup request. This is usually include, if you look into here, RRC connection request. If you remember in RRC connection request, we have usually the user send his NAS identity or they call, for example, he sent what is my NAS identity, which is, for example, it can be STMZ or even random value. The selection of STMZ or random value, and I will explain why we need this kind of values. It's very important as well. But STMZ or random value, it will be STMZ if the user was already registered or already have a registration on this particular tag with the network, so we already know what is his STMZ, which is the identity of the users. And this, when I say NAS identity, this means it's known up to the core network. Or random value, in case he the first time to access, so he will initiate any random value, which was the specific ranges to the NLP. So what will be the use of this? I will explain shortly. But now, till here, we are assuming that the RACH procedure is already successful, and the user now is uplink synchronized. We have these three steps: message 1, message 2, then message 3. So assume now, in case we have another user here, and this user initiated the same message, was called PRACH as well, but somehow the user used the exact same frequency time offset and something called preambles. For example, each of these messages PRACH is initiated through something called preamble. We have a preamble that's kind of a signature for the message. We have a preambles from 0 to 63. This is kind of a code, or yeah, you can say a code or signature being used to differentiate between the users. For example, one user can use PRACH 0, the other one can be used PRACH 1. In order to differentiate, the NLP can differentiate between these users and they can reply back to them. So each user should, in normal case scenario, should use a different preamble sequence. For example, 0, 1, 2, 3 up to 63, as I mentioned. But during the initial access, we have two times of RACH. I'll discuss later about it. It's just we use something called CBRA, or Contention-Based Random Access Preambles, where the preamble is randomly selected by the users during the initial access. There is no any dedicated preambles. The NLP cannot instruct the user to use a specific preambles, so the user initiates random preambles. So the probability to get two users or several users initiate the same preambles at the same time, this is exists. So here I'm assuming this example that UE2 initiated the also PRACH using the exact same preambles. So now there is a conflict here. So what will happen? The NLP need to again send for them the same exact same information because it received from two users the same preambles. So the NLP will send again timing advanced command and RA-RNTI to the same users, the same user here, and the same will happen from here. He will send again each user will send his message 3 or RC connection request to the NLP. So till now, one of these users should be try to reattempt after the failure. For example, the NLP should differentiate between these users because only one of them should access at this time. Since both of them use the same preambles at the same time, so only one of them have to access. So what will happen? There is something called MAC contention resolution or message number 4. This is MAC contention resolution actually. It will be used by the NLP and it will be sent for both UE1 and UE2 to let them settle the conflict or the confusion between both of them, to tell them which one of these users are the winner, which one is his message 3 is successfully decoded, and which one is failed. So this is MAC contention resolution CRNTI. What exactly indicates? For example, here in this one, it contains something called CRAI or contention resolution identity, which is actually the user will take the message within the message number 4 here and compare it with his own STMZ or random value. If it's matched with whatever exists within the MAC contention resolution message, which is the CRAI, which is again called contention resolution identity. So if this identity shared in this message match with whatever being sent before within the RRC connection request here, the identity in RRC connection request. So this means that this message 3 is being successful, and this means, for example, that UE1 is the winner, and his message is being successful, and now his temporary assigned RNTI will become a permanent or becomes something called CRNTI, and this will be used later on during the scheduling and all the time between the NLP and the user. And by the way, whenever you try to open any traces on a particular user, we use this one, for example, baseband traces or whatever. And if you don't have any MZ information and you would like to trace a specific user, so you use his CRNTI. So you now know that CRNTI can be founded, you can find it within the MAC contention resolution, or even within message tree sometimes, or within the RRC setup, which is come later on after the RRC connection request. So what will happen for the other user actually? The other user, what will happen if you look into the other user? Now the other user will check the STMG or random value. If it doesn't match with the CRAI, so he will consider RACH as a failure, and now he will repeat or make another a new RACH request in another different timing, and I will be explaining as well the parameters controlling the retransmission of the RACH whenever there is a failure. So this was a high level perspective about, you can say, the call flow, but from high level perspective here. So what else we have? If you look into the right side here, this one. This is just a quick visualization for all the parameters where we are going to discuss. So I split it into 4 points. Point number one is related to the frequency offset. As I told you in the message one here, this is called message one. Usually here, the user doesn't have any previous scheduling or any previous information telling the user, I mean PDCH or any grant telling the user at which resources, right? So there should be something in beforehand telling the user exact locations or in the frame or in the frequency where he's going to use his PRACH, the first match message, right? And I told you this, you'll find it within SIB2. So one of the first parameters is called frequency offset. You will find, for example, this frequency offset have a range from 0 to 94. So, for example, it will tell him that your frequency offset, for example, in this one here, you will find it within SIB2, is telling him 7. This means the PRACH can be sent at resource block number 7. Because here, for example, resource block number 0, you have an offset 7, so you will be, or 6, you'll be starting from RB number 7 here. And usually the RACH is fixed with 6 resource blocks. So now he know that you will be starting from RB7 till RB12, because again the RACH total number of resource blocks equals 6. But still he don't know at which subframe, right? So there'll be another information, something called slot configuration index. This will indicate to a piece of information. This one telling him what is the start subframe number. So for example, here is telling him your subframe number starting at subframe 2, which is subframe 1, then to here at this area. So you know that he will be standing here at subframe 2. This will be his start point, and at resource block 7. So this will be his start point. Then there is another information also you can indicate it from the PRACH configuration index, something called PRACH format. Whether it's long, whether it's have different types from 0 up to 4, 0, 1, 2, 3, and 4. So, for example, assuming that and each one have a duration. This duration is saying, for example, this is PRACH format here, telling us duration of the sequence you are going to generate. For example, message 1, let's have something called preamble sequence. Like, for example, how long it takes to generate or to format or generate the first message number 1. So here it's telling it will be 2 milliseconds. So you know that he's starting here, but he need to stay for 2 milliseconds here, right? So now he know that this area now based on these 3 parameters, where he can use it within this frame to send the message number 1, right? This is how we get from the SIB2. Later on we'll go into more deep dive. Point number 4 here is, again, as highlighted, I told you that, okay, here we identified the frequency and the timing to send the first PRACH message, but the user still need to know at what preamble is going to send. As I told you, this preamble is kind of a signature for each user to differentiate between the user. We have from 0 to 63, we have 64 preambles in total, right? From 0 to 63. And usually the users select them randomly, but still within the contention base, which is used in the initial access. There is something called group A and group B. So the user need also to know what, okay, he's going to select randomly, but it will be randomly either from group B or group A. This is also controlled within the parameters. I will explain all this in details, and I will explain why we need this kind of information about group A and group B, and what is the use case by the NOB for this kind of information. So yeah, so now let's move to the next part about the high-level call flow, or the call flow in more details, and also about the RACH types in general, not only limited to the initial access. I will also give a quick high-level introduction about the different RACH types, something, for example, CIFRA, Contention-Free Random Access, just to have complete information about random access procedure. So let's move now to the next part. So this slide again, it's covering the RACH types and the call flow in general, right? Call flow. But I would like first to give you a quick recap in case you don't know about the RACH in general. This would be good information for you to understand. That in general, again, RACH, as I mentioned to you, we already completed the cell selection now. So now the U, as mentioned here, can be on suitable cell. And now before any RRC setup or attached, the user need to get first access through the RACH procedures to achieve the uplink synchronization. And the stuff to establish the signal radio bearer or the SRB with the NLP. So again, usually we use something called CBRA. But what is CBRA? What is CBRA? What these kind of things? And I want just need you to understand it, just for your information. It's not really related to whatever we're going to discuss at the end of this session or during the complete session, but just for complete understanding about that part. Usually the random access procedures, which is again needed to have the link synchronization with the NLP, have two categories or two types. Something called CBRA or contention-based random access, and the other one contention-free random access, which is CIFRA, right? So what are the differences between both of them? Okay, each one of these have a different use case. For example, the CIFRA can be used in a specific cases, and CIFRA can be used in a specific cases, or CIFRA can be used in all cases. This is just to have a very precise information. CIFRA can use for in all the cases within the 4G or either the 5G, while CIFRA can use at very specific cases. What is the difference between both of them? The first one is called contention-based. As I told you, usually have a 64 preamble, right, from 0 to 63. I told you in the previous slide that the user, the first message he's going to initiate, usually select a random code or a random signature. Let's assume the user 1 will select preamble 0, user 2 will be select preamble 10, user 3 here and there. So again, there is a probability for a contention or a conflict, right? So maybe two users will be selecting the same preambles because they are selected randomly. So this might cause a failure or conflict, as I discussed in the previous slide, right? So this is the first time. It's just based on randomly selection of the preambles. While the contention-free preambles, the main advantage of that part that the UE himself doesn't initiate randomly. The NLP first need to instruct the user, telling him exactly what preambles you should select. What the NLP do this? It do this to avoid any conflict with other users, and this information mainly can, or this scenario maybe mainly can be done in case of the whenever the context of the user is being known by the NLP. For example, if the user is already connected in the network and the context of the user being known by the NLP, so the NLP can send him information beforehand to tell him or to instruct him what kind of preamble is going to use to avoid any conflict. So if you look into the, for example, this particular table, this is summarizing the overall use cases. So for example, here is telling initial access, which is our main discussion today from RRC idle mode. This is mainly used CIFRA. The CIFRA doesn't support this part because again, the user doesn't yet have any context or the network doesn't know any information about the user yet. So it cannot assign any dedicated preambles or a specific preambles, right? Also, whenever you transition from an RRC inactive to RRC connected, RRC inactive and RRC connected is more known in the 5G, but it was also introduced in I think from release 13, if I remember correctly, in the 4G as well. So, for example, you are already inactive and connected to going to connected mode. Also, this is using the CBRA board. Same for RRC connection establishment. In case if you lost your connection and trying to do, they just trying to initiate a new RRC connection establishment using CBRA. And during the handover, this can be used CBRA or CIFRA. Again, you know, handover means I'm moving from source to target. So this means already the both source and target have the information about this particular user. So they can assign for them a dedicated variables to avoid any conflict with others. And that's very, very important for the handover because we need to avoid this scenario of this kind of conflict during the handover because user already in connected mode. So this might lead into a longer interruption in the data session in case there is any data session ongoing during the handover. Same if you have a downlink data arrival and the user was out of sync. This is also can be being used both CIFRA and CIFRA because already again, the user already in downlink data arrival is coming and the user is out sync. So the NLP already know that this user here it can address this user because it already have some information about this user in downlink, especially downlink. In the uplink, if uplink data arrival and the user is out of sync, so only this CIFRA. Same for the previous two or the next two messages For example, here this is during the cell addition, but this is also supporting the SIFRA, which is during the 5G non-standalone. And as you know, during 5G non-standalone, you already have the information or the context already exists because 9 standalone mainly rely on the 4G network. So you know that Yuri is already connected to 4G, but now he's trying to initiate the SGNB addition, or even I think during the carrier aggregation, not only the SL addition, not only the ENDC or um, the so-called the NDC or the 5G standalone addition. So this is the main differences from the call flow perspective. I already discussed in the previous slide about the contention based. I highlighted to you that there is a random access message being sent from EU to unit B, which is message one. Then will be a response with RAR. I'll discuss in more details next slide as well. Then we'll have a message three, which is usually the RRC connection setup request, which is called schedule transmission. Then you will have a message four here, right? Coming back from unit B to the UE in case if there is any conflict with other users. So the unit B need to differentiate or need to solve this conflict. In case again if two users sending the same random access preamble message with the same preamble which is from 0 to 63. So this MAC contention only coming whenever there is a contention or conflict between different users. Okay. The main difference between SIBRA and SIFRA, if you look into this bottom down here, if you look into here, for example, SIFRA, this is initially the first message. Message one will not come first as this one. They need be first need to assign random access preamble assignment to the user. For example, tell him don't send me RACH message one randomly. Don't tell me, for example, I'm sending a preamble 0. No, I will. The input be telling him exactly which preamble. For example, tell him use preamble number 5. So the user will exactly use the same preambles, and in this case, he will initiate again with the same exact procedures, which is message 1, then message 2, then message 3. But the main difference is you will never find this message number 4 in case of the SIFRA, because as I told you, SIFRA or contention-free random access, there is no conflict or confusion. So we don't need this kind of message number 4 to differentiate between two users, right? So this is the main differences, and this was a high-level view. Now we'll go through now more details about this part, about the SIBRA, about more details. I will repeat again the same call information, call flow, but I will just include some more additional information. Then later on, we'll go into the contents of each and every single message, message 1, message 2, message 3, what kind of content within these messages, in case you didn't see before, so you understand about the signaling content of all these messages. SIFRA will not be covered because this is not related to whatever we are discussing. I'll just give the main idea here was to give you a complete understanding about the different types or categories of the random access procedure. Now let's move to the next slide about the contention-based again call flow, but with more deep dive. So again, this is the contention-based random access. This is exact whatever we discussed in the previous two slides about the code flow, but I just added additional information here inside or bottom the messages just to indicate high level information about the content. I will again go through them with some values later on, but just give you consider this as the introduction for the message contents. So, for example, again, we highlighted once the user completed the cell selection and downlink, already find the best suitable cell. Now he need to initiate the contention-based random access procedure in order to get uplink synchronized or synchronization, and also to get the first or the resources for the first RRC messages. Because once you get uplink synchronized, now he can get the resources. He can now start doing, for example, upload or replying back and forth to the input. So again, if you look into this first message being sent by the user to input B, it include the preamble index. For example, as I told you, from 0 to 63, it's telling him I selected this preamble 0 or 63 or whatever, and also it contains something called RA-RNTI, Random Access Radio Network Temporary Identifier. This is an identifier mainly used or sent or designed by the user. I will be discussing this in a detailed slide later on. Design or formulated or designed or generated by the user based on the frequency and timing information which is being shared or discussed before in system information block type 2. It will be sent by the UE to the input B telling them this is my RA-RNTI. Please, if you are replying back to me, you need to address me by this part to be able to decode the second message. Otherwise, I will not be able because still there is no any identifier being generated or assigned by the input B to the user. So this is called random access radio network temporary identifier. It's mainly used to identify the user within the random access response. So this is the information. Usually you will find there is a ground message will be coming, BDCCH, a ground message sent by the NLP to the user. It's just telling him you will expect to receive the random access response at this particular time or frequency, because the first message here is using the PRACH or physical random access channel, while the second message here for the NLP to the user is sent through the physical downlink shared channel. So this PDCCH is used to tell the user this PDCCH or physical downlink shared channel will be sent at which time or frequency. It's kind of you can say it's scheduling or telling them what kind of resources. So you must choose the random access response. This is including different information. It will include RA-RNTI, this message, telling this is for you. So the user will be able to read, understand this message for him. Also, it will tell him what is the preamble index. Here, it will be the exact same information here. Will be added again here. And it's just needed to the user to be differentiate between different users. For example, if random access response is sent and several users received it, so each user will understand this information is mainly indicated for him through these two temporary or these two identifiers. Now the NLP will assign the so-called CRNTI or temporary CRNTI, which will be used only later on for the scaling perspective by the NLP to the user to, for example, give a specific identifier to this user to be able to do the scheduling to this user. And again, we can use this one for the traces. Also, as I mentioned in the previous slide, it will send the initial time advance command in order to tell the user we need in the next message when you send uplink, we need to sync or do some adjustment in your timing whenever you send the uplink messages to be able to have a very good synchronization between the UE and the unit B, because there might be 100 of UEs, or each one have a different distances. So each one have a different propagation delay. So there should be kind of an instruction from the NLP to the user to align the timing between different users and to this particular UE. From NLP to this particular UE. And also there will be uplink access grant. This will be assigning the resources needed to transmit the third message here. For example, this one, it will tell him now the third message for the UE. UE can transmit it at this particular frequency, at this particular frame, but this particular subframe, at this particular system frame number here and there. So this is telling him all the information to be able to transmit the third message, because third message, which is message number 3, it mainly transmitted in this channel, physical uplink shared channel. So this is called message 3. It's called scheduled transmission, which is mainly equivalent to RRC setup request, and this is including the temporary CRNTI, and also including as I told you before, the NAS identifier or NAS UEID. This is it can be STMZ or MZ or random value. Usually it's STMZ or random value. I told you it can be STMZ if the user was already registered in the network before and he already know what is his tracking area code. So you can use the STMZ directly. If there is no STMZ, the user was not registered before, he will just format or generate a random value, which will be used later on during the MAC contention resolution message number 4. And MAC contention resolution, I told you this is mainly needed in case if several users use the same preambles and initiate the same message 1 with the same exact resources. So this is the type here. It should be number 4. So this is message number 4. It will be sent mainly by the NLP to different users in case if there is a conflict. As you can see here, finally, NLP sends message for contention resolution to resolve any contention and confirm the UX. This is if available. Sometimes it might not need it. So, for example, if two selected the same preamble, as I told you, preambles from 0 to 63, both of them, for example, selected preamble number 5, then the non-matching UE retries the unknown procedure. So whenever the user which is not matching with contention resolution ID, now we initiate a new or retry new access procedures. The one which is being successfully decoded the contention resolution ID or contention resolution message, he will now convert the temporary CRNTI to CRNTI. Otherwise, he will rebuild the random access attempt. So actually, this will be like giving again introduction to whatever we're going to see in the messages content, but the message contents later on will be also including more details. So actually, before I jump into the parameters details and discussion, I would like you just to give you a quick introduction about something called U identities, which is mainly assigned by the user or by the NLP or between both of them in order to get to be able to identify or differentiate between the different users during the scheduling or the initial access or the paging and these kind of things. So you have many different types. For example, the first one called paging. This is mainly used during the paging. This is used using the idle so the this helps the user, for example, to find, decode the paging messages. So we have multiple here. I will not discuss all of them. I'm just giving here for information. But the main messages which we usually needed during the initial access, which I already discussed almost all of them. For example, the first one called random access RNTI. This is used during the random access response, and this is during like whenever again the would be sending a random access response message, the user is like generate this RA-RNTI to help the network answer a UE who's trying to access the cell during the random access response. I will discuss this with one visualization example next one because this is very important one. The second one is temporary CRNTI. Actually, in general, there is a CRNTI already in network temporary identifier. This is usually used for the dynamic scheduling by the NLP to the user. Usually, the NLP need to assign this kind of identifier to the user to be able to schedule these users, and the user will be use this identifier also to decode any BTCH or any other information whenever there is a scheduling. So each user can be differentiated by this particular RNTI or CRNTI. Initially, we start with the temporary whenever the user is coming from the very beginning, as I highlighted before, during random access response. Once the user is being confirmed and he accessed completed the random access response, this temporary CRNTI will be converted into CRNTI. So what I need to discuss in more visual example is this one, just to tell you exactly how it works. So this will be the next slide. So let's see what we have in the next slide, which will explaining exactly how this RNTI is being next two slides actually is being first of all generated by the user and how it's being used by the NLP and the user or BTS and the user to decode the random access response message. So if you find this slide, this is mainly, if you look into the title is saying RANTI. It's mainly telling you or answering one question, how the user find message 2, even though there is no yet any temporary identifier assigned by the network. And this is actually RANTI is this question. For example, the core idea of RANTI or Random Access Radio Network Temporary Identifier, that this is like mainly calculated or derived from the preamble in a specific RACH subframe and resources. For example, whenever the user is going to initiate message 1, he already know at what frequency, at what subframe, at what is the duration, these kind of things, right? Especially the subframe and the frequency, correct? So there is a formula that will be used by the user, which is this formula in the left side here, right? It will be used by the user, this formula, to calculate the RA-RNTI in order to include it or to tell the network, or the network himself already know but it should be included the user in message 1. It will tell the network, this is my RNTI. Whenever you send a random access response, please include it in the random access response message in order to be able to find this message 2. So what is the formula? This one called 1 plus TIAD. TID, this T stands for time, which is actually the subframe index. And FID, this is frequency domain index. And it has a range from 0 to 9, which is normal because subframes, we have 10 subframes, or frequency domain index from 0 to 5. So in general, in FDD, this frequency index is 0. So the formula will be only 1 plus TID. So for example, if message 1 sends subframe 2, this means our RANTI will be 3. So this is how the user can calculate it. But again, by the way, you can find different users using the same RNTI. So that again might sometimes cause a conflict, but it can be differentiated later on using the preambles. And in case if the preambles also there is a conflict, then it can be later on differentiated, or the conflict or the contention can be solved through the message 4 as we discussed before. So this is the sequence. Initially, the user send the preambles and a specific subframe and resource. Then the user will build the RNTI based on this PRACH time and frequency, and maps to one RNTI based on the calculation on the left side here. Then once the user send message 1, the NLP will be sending the PDCCH resources, and within the random response message, there is something called response window. This is one of the timers. I will be explaining this one in details later on. the UE checks the subframe for this one who's scrambled by relevant RNTI. So the user will be able to decode the PDCH based on the RNTI. Then the user also will be able to identify now message 2 again based on our RNTI. Later on message 3 and message 4 we have now the CRNTI or the temporary network temporary contention or CRNTI, which is used by to be assigned by to the user or PTS to the user, but this is mainly used during the random access response. And this was the explanation for that part. Next slide quickly. Here, this one is just explaining or visualizing how this works. For example, here, this is assuming now we have an uplink frame, you have a downlink frame and downlink from here, right? And downlink from here. So this he means the user here will be using this part, right? So here I'm assuming, for example, that here 3 users sent at this particular subframe. They send RANTI3, all of them using the same RANTI. Okay, but each one of these users using a different preamble. This, for example, using preamble 5, this using 2, and this is using 9, right? So now what will happen? If you look into here, this is the preamble transmission already done. So there is a timer will be starting. Usually it's coming after a particular timer here, for example, after 2 subframe. I don't remember the exact number. So here there is, first of all, there will be a scheduling from the NLB to the user in downlink direction through the physical downlink command controller channel, sending this like to get the user to give him the grant, uplink grant, to tell him, or down uplink grant or the downlink grant, sorry, to tell him the BDSH or physical downlink channel for the random access response will be sent at what resources. So that this response window, it's a timer will be started for these 3 users. So in this response window, now the users will decode this BDCH or physical downlink command control channel based on the RANTI3. So they will be able to decode it. Once being decoded, all of them can now decode or read the random access response for E1 to 3, and it will be differentiated now. There is no conflict because each of these users are using a different RAIP ID, which is the random access preamble identity, which is again from 0 to schedule 3. Same idea for this UE4 and 5, was using the same RNTI, but using again same random access preamble identity 1 and 9. So now again, another timer will be started for this user for response window time to try to decode the physical downlink command control channel. And again, now they will be able to scramble the bits based on the RNTI8, which is this one, right? This one, which is being scrambled here for the physical command downlink command control channel. Then again, afterwards, they will be able to decode the random access response match. So this is a use case of the RANTI identifier. Now let's move to the parameters to get more high level first about SIB2, then we'll discuss each and every single parameter in details. Okay, just a quick recap. This slide was already presented in the previous video, in session number 1. A quick recap about the sales information acquisition, because now we would like to read the sales information block type 2 to get all the relevant or related parameters to the RACH procedures, right? To help the user initiate the first message number 1. So here again, remember always, whenever there is a system information acquisition during the cell search or cell access, the user first uses master information block type. Then from this master information block, it will get the information about system information block 1. So now it will be reading system information block type 1. And here you'll find information to know where you can find and read system information block type 2. And this is our main discussion today, which is the second one here, right? Which is common radio. This is mainly contains the common radio resource configuration, including RACH and relevant parameters. Now let's jump to the content of the draft test of the parameters, giving a high-level introduction, then jumping into each and every single parameter description. So now, after the user decoded the system information block type 2, now he is being able to decode or read or find all the RACH-related parameters, right? So if you look into the figure in the left here in the middle here, this figure, this actually mainly contains all the parameters related to RACH within system information block type 2. If you look here, this is from the draft test. Actually, just one important point to highlight, system information block type 2 also contains many multiple other parameters If you look into it, for example, some parameters related to broadcast channel, paging channel, physical downlink shared channel, physical uplink shared channel, physical uplink command controller channel. But here we are just addressing for now the parameters related to the RACH. So usually the parameters related to the RACH are being like classified or categorized into 4 categories. If you look into here, the first category here, which is point number 1 here, which is highlighted by this color. If this is mainly answering one question, which is saying first, when preamble which preamble can I use? If I remember, I told you usually the user transmit message one using a random preambles, which can be from 0 to 63. However, this is still can be controlled and it have many other also parameters. For example, if you look in here, we have 4 parameters. These 4 parameters answer the question where which preamble the user can use. Okay. For example, here is telling him what is the total number of preambles he will have for this contention based. This is mainly for the contention based. Like what is the total? For example, here I can say I can have all of them to be used by the contention based. Then here is saying that this contention based classifies into 2 groups, group A and group B, and each of them having a criteria which one to select, which one the user can select. This will be discussed more details later on. But the first category of the parameters answered the question was saying which preamble the user can use, either 0 or 63 or whatever, okay? And what kind of ranges we have or allowed for this particular user. So it give him a set of allowed preambles with some criteria so the user can do the calculation and then select the particular preamble. Then point number 2 here, which is one in the bottom down here, which is related to the RACH planning, right? This is just answering a question was saying that the user might ask or you might ask for ourselves, when and where can I transmit message number 1, right? Like message number 1, which is, if you remember in the call flow, it was random access preamble. It had many different parameters. All these parameters just simply defining the time and frequency, which I even explained in the very beginning, telling the user at which time and frequency he can send the first message, which is message number 1. I will be explaining some of these parameters in detail with some visualization later on, but just this is a quick summary about the content here. Then we have message number 3 here, or the category number 3, which is mainly consisting of power ramping related parameters, which is mainly 2 particular parameters. Actually, this is answer a question that the user or we might ask, at what power should I start and how should I increase if needed? For example, at what power should the user start initiating the first preamble? This is mainly identified by this particular one. It's related to uplink power control. Preamble initially receive target power. This is just identify at what power the user should start. In case of any failure, the user need to know at what level I should increase my power. This is based on the second parameter, and also I'll be explaining some of these parameters with some visual explanation to make it more clear to you. Then the last part, which is point number 4 here, is related to random access supervision information, okay, or parameters. Actually, this is answering a question that what should I do? For example, if what should the user do or what should he do uh, uh, if there is a RACH failure or if the network, for example, didn't respond to whatever messages the user is being sent. So this is mainly controlling the supervision parameters, which can do, for example, waiting time for a specific message or retransmission, maximum retransmission allowed, how much he can stay or do the retransmission until he considers as a radio link failure for different messages, can be message number 3 or even the preamble transmission, which is message number 1. Also some timers related to the waiting timer, for example, for MAC contention, which is message number 4, or other random access response, for example, which is message number 2. So all of these parameters will be now explained in details one by one. Then we'll be ending by showing the content of message number 1 to message number 3, as we did before, but in high level. Now we'll go in more deep details. So now let's try to cover these 4 categories with different parameters with some good visualization. Okay, this section actually is covering the first part, which relates to the planning parameters. This is the first parameter we're going to cover, which is called PRACH frequency offset. Okay, so this is first of all one of the planning parameters. So there is this parameter called PRACH frequency offset. This PRACH frequency offset have a range from 0 to 94. So what it means by this parameter? Actually, this parameter simply, first of all, from high-level perspective, is simply identifying at what specific frequency the user can transmit message number one, which is the preamble random access preamble. Okay, so as I told you, it's a very simple one. For example, assuming this is your frame in terms of time and frequency. So, for example, this y-axis is a frequency domain, and this is, for example, the first resource block 0, right? So, in case of the FDD, especially for FDD part, it's saying that this parameter is just explicitly specify or indicates directly gives you the first uplink index, as you can see, used by the PRACH. For example, in this particular example from the draft test, the resource box was number 7, right? So this is telling you that you will, as you can see, PRACH 7, so your PRACH will start at RB7. So this directly telling you that your resource block will be starting at RB7, which is here. You'll find your first message or resource blocks coming from here. And in total, we have fixed 6 resource blocks used for RACH. So now we know that what is our start point, and we know that this will be our resource blocks. But there is some very important information in terms of optimization. You need to understand it for this particular parameter or consideration. I can say it in other words, that if you read into this sentence, that it's saying the main objective when configuring the frequency offset, which is this parameter, is to avoid the fragmentation of resource blocks available in the physical uplink shared channel. For example, the orange part here, this is uplink shared channel. So the main idea here that they don't want to keep this kind of space. So usually the best scenario is to keep the PRACH resources adjacent to the PUCCH or the physical uplink command control channel. So for example, to give the offset or this PRACH frequency offset as, for example, RB4, which is here, to change it to 4, to keep it adjacent, similar to this one. For example, this one have a different offset, but it's directly adjacent. So there is no space. So your channel or your resources for the physical uplink channel, shared channel will not be fragmented. You can just take it as one shot, right? So this is one of the consideration which can indirectly improve your uplink throughput as well. This is one of the main consideration here. So this was the first parameter related to the planning part, related to the PRACH frequency, where it's identifying at what frequency and where and at what frequency the user can transmit the first message, which is message number 1. Now let's move to the next part, which is continuation for the RACH planning parameters. So the second parameter for the RACH planning, which I'm going to discuss now, is called PRACH configuration index. This one you can see. So from draft test, for example, this is showing us value number 5, right? So what it means by PRACH configuration index? Actually, this is just simply defining, for example, your time, at what subframe, for how long the user can transmit message 1. So the first parameter, which is PRACH frequency index, it's identified your frequency. So PRACH configuration index is identifying the timing in terms of which subframe and what is for how long he can generate the message 1, which is random access preamble, right? So how this works actually? It's very simple. It might look complicated whenever you read it, but I'm telling you it's a very, very simple parameter. For example, this parameter, once the user read or find this parameter in SIB information block type 2, which is this one, he will find this part, 5. He will go and look into a 3GPP specified tables, which will be saved. The user already know about it. He will go and find where is this 5 indicating. For example, this is a complete table, but I split it into 2 parts. So the PRACH configuration indexes starting from 0 up to 63. You can see each one have equivalent parameters. For example, this PRACH configuration index, it now can identify the system frame number, like at what system frame number the user can transmit message 1. So for example, if here I'm telling it's 5, so this means you will be transmitting a system frame number 7. So this means that, for example, if I go back to the previous figure, this one, this means, for example, here I need to count 1, 2, 3, 4, 5, for example, 6, 7. So you know that it will be transmitted here as subframe 7 as an example. Okay. So this is the first part. Going back here, PRACH configuration index. The first part to do, it's just refer to the subframe number, right? So here I know that this particular example is referred to subframe number 7. So this will be my start point. The second part as well, which is defining for how long the PRACH can be generated. This depends on something called preamble format. I have another slide, next slide, to explain in more details. So, for example, here you have usually 4 types or 5 types of preamble format from 0 up to 4. So, for example, here you will find that the ranges from 0 to 15. This is equivalent to PRACH format 0, and you have here 16 up to 31 PRACH format 1. Then you have PRACH format 2 and 3. Each one of these PRACH format have a specific length. For example, that's telling you that your sequence, preamble sequence, can be generated, for example, in 1 millisecond, or 2 milliseconds, or 3 milliseconds, here and there. So there is kind of, and also giving you the PRACH format, as I will discuss later on, giving you like kind of a planning flexibility. For example, some of them using a long preamble, you can have some so-called root sequence indexes or root sequence up to 839 or up to only 138. So I'm not going to discuss this in much details, but just give you quick information that the preamble format, as I will discuss in the next slide, is just identifying 2 parts: the length of your sequence or preamble sequence. For example, your preamble, which is generated or used in message 1, how long it will take, 1 millisecond, 2 milliseconds, 3 milliseconds, and also what is your planning something called rich sequence indexes, for example, up to 837 or whatever. This is the main idea. So again, the PRACH configuration index, mainly the main important part here to identify subframe number, at what subframe I will start, for how long I will stay. This is the main idea. So this is now to get a complete figure. I will explain this one in separate slide, next one, just to give a complete figure about the time domain. So now we understand that the user will start at subframe 7 or initiate message 1 at subframe 7, but we don't know for how long. For example, in the previous second I showed 2 milliseconds. Now I need to know it will be 1 millisecond, 2 milliseconds, 3 milliseconds, how long. So this is based on preamble format. So now let's move to the preamble format, which is in the next slide here, to explain it more. So if you look into this preamble format here, usually have, if you look into the down table here, okay, I categorized into from 0 to 4, which is 5 formats. But first, before doing anything, just let's read this one. PRACH format defines the preamble structure and time. Each format is made of cycle prefix, sequence, and guard time. This is just the construction or the structure of the preamble. Usually, the preamble, which is 0 to 63, is consisting of cycle prefix at the beginning. In the middle, you have a sequence, and this sequence has a specific duration. Then you have a guard time. And in general, we have we have 5 formats, 0 to 3 called long preambles, while preamble format 4 is only used for TDD. This one, preamble format 4. The longer format, as mentioned here, support usually larger cell ranges. So this is the trade-off actually, that whenever you have a longer format, for example, from 0 to 3, we can support higher cell ranges, as you can see in this specific range. For example, format 0 have up to 15 kilometers, while format 3 have up to 100 kilometers. So depending on your cell type, you do the cell formatting. And also there is a trade-off with the overhead. For example, if you look into preamble format 0, which is our case now, based on the PRACH configuration index here, we used to have 5, right? So we used preamble 0. This means here I have, first of all, up to 15 kilometers only, but the duration is only 1 millisecond, which means in the frequency domain and time domain in the frame structure, I'm only using 1 millisecond subframe. This means you will have much less overhead compared to the other two. So this is reducing your overhead, and still you're having a good cell range to cover. So this is depend on your main use case. For example, this is main use case used to small to medium cells. This is also another thing. So here is saying you that the user doesn't choose the format by itself, while watch for parameter identifying, the one we discussed in the previous slide, which is called PRACH configuration index, which is broadcasted within system information block type 2. And this tell you usually what is the preamble format and the allowed PRACH subframes. For example, in the example here, in the draft example, we have 5. It's referring to PRACH configuration index. It's referring to preamble format 0, which is indicating that the total length of our preamble would be 1 millisecond, and it will be starting at subframe 7. So this means you will have only subframe 7 used for the transmitting the PRACH format, preamble, the first message, which is random access preamble. In case if you use PRACH format 1, for example, this means you will be transmitting your random access response in 2 subframes. So this will increase or double your overhead, right? So this was the main idea. So the first 2 parameters, which is the PRACH frequency, then we discuss about the PRACH configuration index, one, identifying where and what frequency the user is going to send, and the second one is defining when at what time the user are going to send the first message, which is the random access preamble. Now let's move to the next parameters. I just added additional one slide just to quickly give a high-level introduction, but not going into a deep dive details of the remaining RACH planning parameters. For example, here I'm discussing about if you look into this figure here, there's something called route sequence index, this parameter, right? And this parameter called, for example, here, for example, you have the zero correlation, right? And also the high speed flag, okay? So actually what it means by the route sequence index, for example, the one I'm discussing here in general. Actually, there is something called route sequence index, which is usually called the cell pattern. Actually, usually you have different route sequences up to 839 here for the long preambles. For example, if you're using preambles format 0 to 3, you have long preambles. They have up to 839 sequences. What it means by these sequences? For example, usually they saying the main definition that the root sequence can generate, if you read this statement, one root sequence, for example, one of these root sequences can generate multiple preambles, depend on the other parameters which called, for example, zero correlation configuration, which is this parameter here. It was also part of the planning, which is control something called cyclic shift, which is control something called NCS and here and there. For example, if here is saying that if the other parameters of which is called zero correlation is using a small cyclic shift, this means you have more preambles can generated from this particular root sequence, but the supported cell range become smaller. So let me give you a practical example. It's telling you, for example, if you have a long preambles and the root sequence and preamble equal 839, this is for the long preambles. We know that long preambles having up to 839 root sequences, and the cyclic shift, for example, defined as 38. Okay, the cyclic shift again is mainly controlled by something called zero correlation zone. I will later on, when you go further, I will attach one Excel, which is showing some of the planning calculation for the RACH planning. For this zero correlation, for example, here equal to 9, so this is equivalent to a specific cyclic shift. So here I'm assuming it's 38. So if you divide it 39 by 38, it's telling you that you need your one preamble sequence, the one root sequence can generate up to 22 preambles from one root sequence. So this means one cell needs how much to generate the total preambles. We have a total preamble 64, right? So he divided 64 by 22. This means you need at least per cell 3 root sequences index. So for example, one cell can use 0 up to 3. So you should make sure that you are not causing any planning conflict with others. Because if the neighbor cells are using the same exact root sequences, which is differentiate between one cell and another, or a conflict between one user and another, even if they can use the same preambles but different root sequence index, there will be no conflict. So if you're using the same root sequence index, this means you will be generating the same preambles with the same root sequence index, which can cause kind of confusion. How? Let me explain this one. For example, here I'm assuming that each cell, for example, need at least a range of 10 root sequence index. For example, this one starting at 0, this one 10, this one 20. So I'm assuming you need 10 root sequence index or root sequences, yes, root sequence per cell, for example. So this means if this one you reuse anything between, if any neighbor cell, even this one to this one, used, for example, something from 0 to 10, for example, 5 or 6 or the same one, this might cause a conflict or a confusion. Let me explain with a practical example. Here, for example, all of them are well designed. There is no any problem, or each one are using a different root sequence index with a space of 10. So, for example, these two cells here is using the same root sequence index, which is 10. So what will happen if this user is initiating one preamble, and both of them using the same root sequence index? So what will happen? Even this one user is connected here to this particular cell. So still, what will happen if this was incorrectly swapped? The init B2 or BTS number 2 may also falsely detect as a valid preambles. This is what will happen if they use the same root sequence index. So what will happen? This one have a counter on the init B side. It will count that I received message 1. Then it will respond to message 2, right? Same here, message 1 and message 2. But for sure, the user will never reply to this one with message 3 because he is not connected to this init B, right? is only connected to this one. So he will just be connected to message number 3, which is here. So this one will be successfully decoded, and this one will be counted as a failure. And this is mainly caused because of the wrong planning. So the summary here, the root sequence index is mainly used, which is this ranges from 0 to 839, just to differentiate between the cells, just to avoid any conflict, and to reuse this 64 preambles in a matter on a smart way. Because if you're using 64 preambles with different root sequence indexes, you will never have a conflict, and this will improve your RACH success rate. So this was the last part about the planning parameters. Now I'm moving the second part or second category of the parameters. The second part here, if you remember, during the system information block type 2, I highlighted also there is another category of the RACH parameters called preamble information. If you remember, the message one the user need to select a specific signature or a preamble, for example, from 0 to 63, right? To select it randomly from 0 to 63 in order to generate the first message number 1. And this preamble or signature mainly used, as I explained before, to be able the ENOD can differentiate between user and another. So still, the user cannot fully or randomly have a complete random selection. What it means by this, there is some many parameters being broadcasted in system information block type 2, which is this one here. I just summarized it here. It's called, for example, number of random access preambles, size of random access preambles, message size group A and power offset group B. Okay. So usually the NLP will give kind of a blueprint to the user, telling him you need to select, for example, preamble 0 or 0 to 27 or 27 to 41, as explained here. Or it can be you have a particular ranges for the contention based or non-contingent based. So how I can read all this. So this is actually the main idea. These parameters can instruct the user to have this kind of format. So the user can understand there is something called group B, which is group A, which is mainly used for contingent based, and also group B, which is mainly used for contingent based random access. And the differences between group A and group B, one of them, this one, is just mainly used whenever the message size is small. Message size number 1 is small, or the user already in a poor coverage. So the init B is just instructing the user to use group A if he has a poor coverage or he have a small message size. So this is just instructing the user to let also the NLP know that this user is in a poor coverage. So there is some parameters which controlling this one. I will explain all of them shortly. The second part, which is group B, which is within the same type of contention-based random access called group B. This is mainly used whenever you have a larger size of message 1 or a better coverage. And as indicating of the bottom down comment here, the main use case of group A and group B, defining group A and group B, this is the main answer, provides the NOB or the BTS with information regarding the quantity of the data to be transferred. For example, this is giving indication to the NOB that or the BTS that the user is going to send a large number of data or small data, and also the coverage condition explained by the user, right? So this information can be used later on by the BTS or the ENB when allocating the resources. So it knows that this user, for example, already in a very good reading condition, so it can, for example, have a better link adaptation or higher MCS allocation later on, especially in the beginning, because link adaptation is not working yet at this stage. So if, for example, you will assign higher MCS or a lower MCS, depend on this user either selected group A and group B. But the question is how the user will be selecting group A and group B, and whether how many, for example, resources or many preambles assigned to contention base. So if you look into this broadcast system which block type 2, this is first parameter is telling him, for example, what is the number random access preambles. This tell him what is the total number of random access preamble used for the contingent based. I will show you the practical example with the exact numbers in the next slide, but just this is a quick definition. Then it's telling him within the total number of the contingent based, how many is used for group A. So this is telling him, for example, I can tell here I'm going to use 50, and out of this 50, I would like to assign 30. So I know that from 0 to 29, I'm using for random access, and the remaining can be group B, or it can be dynamically assigned back to group A if some particular condition is not be used. If you look into this other two parameters here, one called the message size for group A is identifying a specific size for the message. If the message crossed or greater than the size, it will use group B. or if the power or the user already in a poor coverage based on this power offset, the user also will be use group B. So this is a user group selection logic to either decide the user group A or group B is going to be used based on these parameters. So what is this logic saying? It's saying that the user selects group B sequence if both the flow conditions are satisfied. First condition, if the message size is greater than group A message size, which is this parameter actually. Okay, and condition, the path loss is less than the power capability, for example, 23 dBm, minus the target RX power, which is also broadcasted in the system information block type 2, and also this preamble to message delta and the group B offset, which is this one, which is the second parameter here. So all these parameters are being broadcasted within system information block type 2. So the user will calculate the path loss, which is equal to the transmit power, the reference signal power minus the measured RSRP. Then if it's less than these, either the higher 23 dBm maximum power of the user or minus these parameters. So if it's less than this, means user now need to go and select group B in case the message size as well. So the main idea that this is given indication if the user who's group A, this is giving indication to the input B that the user in a poor radio condition. If the user these conditions being satisfied, the user will be use group B. So this is giving an indication to the input B that this user is in a good radio condition. So for example, it can allocate higher MCS, so you can get from the beginning higher throughput. This is as an example. So this would be helping in general in allocating the resource. Now let's jump in the next slide, which is giving you an example, a practical example with numbers with these parameters from the drafter's perspective. So again, this was the 4 parameters I just discussed. This is from the system information block type 2. So you have the first parameter, which is called number and access preambles. If you look into 3GPP, this will be the division. This is mainly defining the total number of contention random access preambles as highlighted here. Okay. So this is, for example, here in this example, if you look into here, you have 52. So you are saying that you have a total of 52 being allocated for the contingent base. This means the remaining will be for non-contingent. You have remaining minus 64. All the rest will be used for the dedicated preambles. Can be used by the NLP later on to allocate a specific preambles to the user, for example, during the handover scenario. The second parameter is the size. So, for example, he's saying that you have a size of 56 bytes, right? So, if the message size, right, is greater than this one, so this might give a chance to move to group B if the second condition, which I highlighted before about the bar calculation is done. So these 2 parameters, which is B56 group A and 10 dB, will decide whether the user can use group B or not. But in general, what will be the classification of the group A and group B and dedicated preambles? You have a total of 52. So I know now that I have a total 52. So the total 52 for this part, which is a contention, will be from 0 to 51. This is for the contention base. And the rest from 51 to 63 will be used for the dedicated preamble or the contingent-free random access preambles. And for the group A, I know that there is a fixed number of preambles that are being used from 0 to 27, right? Usually this one would be from 28 is saying from 0 to 27, right? This is a group A. And the rest can be or cannot be, or depend on the situation, can be used for group B. But group B will be mainly used preambles from 27 to 51. But in case if no condition being for example, achieved, maybe the user also keep selecting group A and so on here and there. But this is giving a chance that I know that any preamble is being selected in this condition will be under group B, right? And if the user is selecting this means the user already in a good radio condition. So you can play around with these parameters values depend on your network planning. So this was the main second category of the preamble information, which is related to the which preamble is going to be selected by the users. Again, it's randomly selected by users, but still there is a blueprint and an instruction can be sent by the user to instruct them to select a specific range of preambles. Now let's move forward to the third and fourth category of the parameters. Okay, the third category of the parameters related to the power. At what power the user should send the message, the first message, which is message number 1. Or in case if there is a failure, at what power he should increase at steps to, for example, to be able to improve the coverage and uplink, to be able to get the message being sent or received correctly by the NLP. So if you look into this one on the left side here, there is a calculation I will just give a quick high-level explanation about it. For the user which is received within system information block type 2, to like instruct the user to calculate what power he should use to send the first message, which is message number 1. So the parameters which we have something called the unreceived target power, which have a range of 190 to 920, and it have a step of 2 dBm. For example, if you are doing the configuration, you will find that the configuration will only accept values by 2 dBm, 99, 92, 94, and so on, here and there. And the other parameter, which is called power ramping step. So I'm going to discuss these two and also the other two, which is called the ramp transmission maximum and RA response window. So here, this is discussing part of the ramping parameters or power parameters, and also part of the supervision parameters, as we discussed in the very beginning of the high-level introduction. So the first part related to the power. At what power the user should send the first message was 1. So if you read this sentence, it's saying that the UE proceeds to transmit the PRACH preamble using a transmit power defined by this particular formula. PRACH transmit power equal to minimum of the PC max. PC max is mainly the UE capability. If the UE capability, for example, as mentioned here, is equal to power class 3, this means using 23 dBm. For example, if power class 1, this means 26 dBm, or power class 2. And also there is up to, if I remember, 30 dBm, but I don't remember exactly which power class. I think power class 1.5 or 1. So power class 2, for example, we use have a higher UE transmit power. So this take the minimum. For example, this is PC max, comma. So this is the second part of the calculation called the path loss plus this defined parameters, right? Preamble receive target path. There is new configuration. So the user will calculate the path loss, which is again the path loss equal to the RF signal, or in not RF signal, the reference signal power, right? Minus the, which is also configuration of the power, your power configuration, minus the measured RSRP, right? So this will calculate the path loss. Then it will add the path loss to this particular preamble receive target power, and this preamble RX target power, it's equal actually to this was not equal to this one directly. This one equal to part. The first part is equal to initial target power, which is this parameter actually. Then plus delta preamble plus other things, which is in case if you have a failure. For example, you have a first failure, so it will do a power ramping step, which is the second parameter here. For example, here I would like to increase my step by 2 dBm or 3 dBm and all. So this step, the power step, will increase more and more whenever you have more failures. We'll see this one with visual example now. So you'll do this calculation, the user will do this calculation, and he will decide at what power he should send the first message in order to be successfully decoded by the NLP. So now the user calculated already. Let's assume the user already calculated the power. He will be sending. He did the calculation. He will be sending the first message, which is random access preamble, right here, as showing in this example. So I'm assuming now it's failed. It didn't being received by NLP. So now the NLP the user now need to wait for a specific timer. If no response by the NLP, right, he need to transmit or make a retransmission of this random access preamble message number 1, right? So now, for example, he will wait for this particular time, which is called RA random response window at MacLear, which is this particular timer. So increasing this timer can give a chance to wait or to give higher chance for the NLP, for example, to receive the message 1. So it can indirectly improve your random access response. Also, it can also have a negative impact to increase the delay. So, for example, this is the window time. In case the user keep waiting here and no response being received, so then now the user need to initiate a second message. For example, here I'm assuming that message 2, it was not this one not either received by the NLP or it's received, but somehow message number 2 was being failed, was not being received. So this timer expired without receiving message number 2. So the user now need to initiate message number 1 after this timer expired, retransmission. So now the retransmission will happen. But if you look into the retransmission, the power here increased by 2 dB because I'm assuming now my power ramming step, as you can see in this example, is 2 dB. This means the power will be increased by 2 dB. So we'll find this space right here, your 2 dB. So what will happen? Now you have a power stamping step increased by 2 dB. So now I will be waiting. If no, also for the same timer, I will start the same timer again, which is this particular RA response window time, which is here. If you look into this parameter, it's equal to sub frame 10. This means I will wait for 10 milliseconds. If no response for 10 milliseconds for message number 2, though the user will initiate a new message, which is message number 1. but now he will increase even the power by additional 2 dB. So now we'll have total 4 dB increase compared to the previous step. So your power increase now by total 4 dB, right? So now the power increase, as I just mentioned, by 4 dB, right? So now I'm assuming that again the timer will be starting the same timer. So for example, I'm assuming now this is one success received this time. So in this case, now the user can start initiating message number 3. And if message number 3 being initiated here, which is called schedule transmission, which is I highlighted before, it's related to the RRC connection request, right? So I will discuss about the related parameter for message 3 and message 4 in the next slide as well. But the last part I would like to explain here, it's about the last parameter here, which is called Preamble transmit maximum here, this one, which is if you look into the draft test, it's here set to 10. This means that message 1 can be transmitted by this particular user for 10 times. If there is a failure, the user will try to do the attempt for 10 times. If it's failed for the 10th time, this then means radio link failure will be initiated, and this means the user will be go for idle mode. He cannot get uplink synchronization. But remember one important point, that increasing this parameter to 10 times or 20 times to very high numbers, this is also in case if you have multiple UEs with a lot of failures, this is also can increase your PDCCH utilization or congestion, because each message one, if it's received by the E node B, the E node B need to do sending a PDCH resources, as I mentioned in the very cold flow, in order to assign the downlink grant to tell the user message number 2 is going to be received at what specific frequency of time for the visit downlink shared channel. So sometimes these kind of parameters, even though it can improve the RACH or degrade the RACH, but also it can have an indirect impact in the other channels, like kind of the, for example, as I mentioned, the PDCCH or even the throughput sometimes. So just remember this explanation. So this was the part. Now let's finalize the parameters in total for the RA supervision, which is the last few parameters. Let's move to the next slide, finalize the parameter explanation. In this slide, we are going to continue with the random access supervision related parameters, which is being broadcasted in system information block type 2. And here we're discussing the last two parameters, which is called, if you look down here, called RA condition resolution timer and maximum HARC message 3 transmission. So what it means by these two parameters. First of all, the current value is being defined here. This one defining the subframes, which can be equivalent to, for example, up to maximum 64. So if you look into here, this is already defined to the maximum, which means 64 milliseconds for this particular time. The second one, this is for message 3, how many times it can be retransmitted for message number 3. If there is a failure of message number 3, how many times can be a retransmission. So, for example, this one is being defined as here, if you look into year 5, and the year of the maximum fail. Okay, so what it means by this? First of all, here, if you look into this figure in the right side here, if you move these already message number 1 being transmitted from the EU to init B, and it will be acknowledged back by message number 2, right? So now the user transmitted again, or first time after he received the random access response message number 2, he sent now the message number 1, schedule transmission, and I'm giving here a number which is 1. This is indicating this is the first transmission. Same for this one. 1 means this was the first transmission of this particular message. So now I'm assuming in this example that the maximum hard message TX3, which is this one, I have a maximum of 3 messages. So I'm assuming now that after the user transmitted this one, he'll be waiting for acknowledgement from the init B to acknowledge that I had received this message through different things. Can be MAC condition resolution, or for example, if the user received later on the RRC setup, he will know that this one already being acknowledged. So for example, here the RRC condition resolution time will be started. I'm assuming now message for condition resolution was not being received. So in this case, this one failed, it not be received, or this one failed, any one of these. But in all cases, the timer expired before receiving the acknowledgement from the user. So the UE now need to retransmit message number 3. So you will do a retransmission. This was a second time to be transmitted. So the maximum transmission of HARC. Now the parameter is set here in this example, assuming it's a 3. So now the user send the second one. He will start again the timer. If this one successfully received, then it's fine. If it's failed, then what will happen? Now this means that the maximum of RA transmission has been reached. So, and still there is no acknowledgement by the NLP side. So the NLP will release, and the user will release the NLP or NLP, sorry, this is the typo, will release the U context and the temporary assigned CRNTI, and the connection will be failed, and the random access procedures cannot proceed forward. So this was the main idea of these two parameters. The first one containing the timers until you receive an acknowledgement from S3. If there is no acknowledgement, there will be a retransmission, and the maximum transmission of message 3 is defining based on this particular parameter. So this was all the parameters in system information block type 2, which is mainly controlling the RACH contention. So through understanding these parameters and the values and how the mechanism, how they work, you can optimize your RACH in a very good way. Not only RACH, if you understand it very well, it can also be reflected in other improvement for other utilization network in case, and this is the main network scenario, as I mentioned before in the example of the physical downlink command control channel. Now let's move to the very last part, which is, again, we already discussed in a high level perspective about the messages contents of message 1, 2, and 3, to go through them just to have a complete story about the random access procedures. And yeah, let's see what we have. Okay, these are the main content of this table on the right side. Includes the most important content of message 1, which is being initiated by the user, which is called usually random access preamble, right? So these are the messages contents. Usually, I summarize this into 3 main questions under message number 1. The 3 basic questions that I should know: which channel was used. So I know that message 1 used this PRACH channel. So this is one of part of the, if you have a drive test or physical decoder of the messages, you will know that the transport channel is RACH and the physical channel is the PRACH, right? So this is, I know, this is the first question I should tell. This is the second one: when and where the preamble was being sent. Remember, we discussed about the parameters can control this one, right? So here, we know that from the PRACH configuration index, the user, for example, should transmit at system subframe number 7. So the red highlight is the most important. Also, this is the physical cell ID. This will tell him I'm camping and downlink in this particular cell ID, which is a PCI. Then also the user from the frequency and time domain. You know now the frequency, for example, based on the, if you remember the phrase parameter PRACH frequency or frequency offset, right? You know now the subframe frequency on this, so you can calculate the RA-RNTI type. So I'm telling him the type of my RNTI radio network temporary identifier is the random access RNTI, and this is the calculated one, for example, whatever the value. So now this will be used later on in as a response from the NLP in message number 2, as you will see in next messages. And also the preamble format. This is already known from PRACH configuration index. And the last part is the identity. For example, he's telling the NLP, I selected this particular preamble, which is 38. And if you recall, the preamble number can classify whether the user falls under group A or group B. So also the NLP will understand this user is under a poor radio condition or under a good radio condition. This is also the main information here. And this is also the system frame number, which is 550. And also, maybe I forgot to mention this one, but in the PRACH configuration index table, if you go back to it, you will find something called PRACH system SFN. It's even or odd. Usually, if it's PRACH configuration index, we refer this one should be in the user should transmit an odd or even number for the system frame number. So this is the main content or the most important content in message 1. Now let's move to message 2. So here, actually, this is about message number 2. Again, I will ask myself some questions. First of all, how did the UE find this response? I explained this one already in details using the RA-RNTI, right? And also the random access identity or the preamble identity, which, for example, was 38 as I highlighted. Which access attempt does the RA belong to? Okay, and what does the network give back for the next step? So this is the content. What kind of information I can find for the next step, for example, for initiating message number 3. So This is actually in simple terms, as you can see, message 2, as you know, it's random access response sent by the NLP after message 1, and it's mainly carrying the uh, downlink shared channel, like physical downlink. It's carried on by this channel, physical downlink, and it's address the user using RNT type. So forget about this explanation. Let's try to understand it from here. So, for example, we know that the input B will be sending this message in the physical downlink shared channel. The input B will be sending this particular subframe, fine, for example. So this is being indicated, for example, it will be indicating already indicated previously in the PDCCH. And here this is RNT type. It's not telling the users I'm adding this particular user, which is using this RANTI number and also using this kind of preamble. So this is now the identification of the users. This is that time advanced command is to this is provide initial uplink timing correction for the EU as we explained at the very beginning. This is in the first message one, it might not be fully synchronized or sync with the init B. So init B need to adjust the timing of the init B through sending the time advanced command. So this is the value of timing advanced value, and uplink grant resources, which is telling the user what kind of resources will being used for the physical for message 3. So allocates uplink resources needed for message 3. So this one will tell him what is the frequency, what is the time, here and there. Then it will assign the temporary CRNTI as I explained before. Here, this will be a temporary one, which will be used later on to address this particular UI. It's used in match 2 RNTI to address the user, but this RNTI will be no longer used. Starting from match 3 onwards, it will be using the CRNTI, temporary CRNTI, and if the user is successful, it will convert this one into a CRNTI, which will be used for the scheduling and access continuation. Here is just information about the transport block size, about the CRC. This is just confirming the downlink block was decoded correctly or not. So this is the information about message 2. Moving now to message number 3. Just very simple. This doesn't have many extra information, but I mentioned at the very beginning that message 3 number 3 in this during initial access is equivalent to RRC connection request, right? Which is usually creating the user identity about the NAS, which can be STMZ or it can be random value as well. As I mentioned before, depending whether the user is being registered in the network or not, before previously registered or not. Also include information about the MME and there might be MTMZ, also the establishment calls. For example, this indicating this RRC connection is being used for the MO signaling, MO data, what is kind of services the user would like to use. Also, this is message number 3. It is identified, like it's addressed to the user by the CRANTI, which is previously being allocated. Like this is we can address the user by this. The user can be used this message or can be addressed by the we can know that this message coming from which particular user based on the CRNTI which is being previously allocated to this particular user, right? And this is giving another information about the channels being used. For example, this transmitted and uplink shared channel direction is uplink. This is FDD. This is subframe number, and that's all the information about the message number 3. So I think we are done today. We almost covered the details of the RACH in many details. Now we'll be just ending about the high-level code flow. In next slide, when you move from RRC idle to RRC connected, and the details of RRC will be covered during the attach procedures in next few sessions as well. Okay, now this is a slide just giving a very high level. Maybe if you already maybe you will be very aware about it. It's not like a big story for now. Maybe the content later on will be covering more details in next slide and next sessions. So from high level perspective, the RRC set of procedures in general is used to establish the signal distributor SRV1. And afterwards, we'll have the RRC configuration, which will establish the signal distributor 2, which include a lot of parameters. So till this stage, before the RRC setup, we don't have SRV, signal distributor 1. So this is the main idea. We can discuss more about the details about if needed. You can drop a comment. I can discuss more about the types of signal distributors, what they are used for, what kind of content, what they are used for exactly. Also, this is used to translate the user from connected idle mode to connected mode. So once this procedure is being done, the user will be considered as a connected mode, and he left the idle mode as well now. And this also can trigger the NAS registration toward the selected PLMN and MME as well. So this now will establish the connection with the core network through the NAS registration. NAS registration mainly, like, there will be a direct communication between the UE and the core network, and the NUB will just be a transparent to transfer this kind of messages. So this is kind of the RRC connection setup. After the random access procedure is being completed, now there will be kind of a handshake, three-way handshake. For example, the UE will first initiate RRC connection request. Then this RRC connection request, as I mentioned before, including the establishment calls and the TMZ or random value, depending on whether the UE has a valid stored NAS identity, which I mentioned before, whether the user was previously registered with the core network and have a specific tracking area code. And once this one being done, this is it will be RRC setup. It will be sent by the UE. This will including the single one establishment, and this will be covering, will include multiple parameters inside that will be discussed later on. Then the user will reply with the last message, which is kind of an acknowledgement that the connection being completed. So this one include just referring to that RRC establishment being completed. Also, this will transport NAS messages transparently, where it includes the MME identifier to tell the NLB that I would like to forward the NAS messages to the specific MME. So within this one, it will have indirect information that it will need to later on to be transmitted to the core network through the so-called NAS protocol, which is including the capability, many different things. Through the NLB will be just, or ENB will be just a transparent, and will be direct communication between the UE and the core network. So we'll be discussing the exact contents in details also during the attach session. So that was all for today's session. I believe we covered a very, very good information in a very clean way and details. I hope if you like the content, share and like, and please drop a comment just to increase the reachability of the channel, and please as well press like and spread the word and share it with your friends. Thank you very much, and see you in the next video.